Systems of linear equations, matrices. Well, you're about to see something or learn something that you wish you had known all along. Because when it comes to solving systems of equations, using matrices makes things really, really nice. In particular, using augmented matrices, I should say. Our objective, solve a system of linear equations using augmented matrices. So let's recall, we've solved a system, we've focused on a system of two linear equations and two unknowns, like down here. And we have solved them with substitution, with elimination, and with graphing. Okay, so now we're going to do the fourth that I've talked about. We're going to solve them using augmented matrices. Recall what we know here. A system of linear equations is a collection of two or more linear equations. And this has been the example we've used several times here. This is the curly bracket or the brace here indicates it's a system of linear equations. And this is two equations in two unknowns. Okay, so what's a matrix and what's an augmented matrix? A matrix is a rectangular list of numbers organized in rows and columns and surrounded by brackets. Okay, so here's an example of a matrix. Here are the brackets. It's a rectangle. In this case, the rectangle is 2 rows and 3 columns. And I have numbers inside. Okay, so 6, 4, 24, 1, negative 9, 8. This matrix has 2 rows and 3 columns. So it is a 2 by 3 matrix. This little time sign is the word by. 2 by 3 matrix. All right, so what is an augmented matrix? Okay, well, an augmented matrix is a matrix, but it's used to represent a system of linear equations. And I have 2 notes here. The equations must be in standard form. So we want, for example, ax plus by equals a number, or ax plus by plus cz equals a number. In other words, variables on the left, constant on the right. In this case, I have 3 variable terms on the left, the constant on the right. The matrix entries in the augmented matrix are the coefficients and the constants. Okay, so what's up here are coefficients and constants. Let's take a look at a real example here. Take a look at a couple examples, actually. Okay, let's write the augmented matrix of each system of linear equations. So here's a system, 3x, this is a linear system of 2 equations and 2 unknowns. 3x minus 2y equals 3, and negative 2x plus y equals negative 2. Notice x's and y's on one side and in order, constant on the other. Okay, so as an augmented matrix, okay, we look at the coefficients of the x terms are 3 and negative 2. The coefficient of the y terms are negative 2, and this coefficient is a 1. And then we draw a dotted line to help us keep things clear, and the constants are 3 and negative 2. So this is the augmented matrix for this system of linear equations. Now you'll notice a few things here. I'll put x. This column are the x coefficients. This column represents the y coefficients. The dotted line is the equal sign. And this column represents the constant on the right of the equal sign. Okay? So these are your coefficients and these are your constants. And that's the augmented matrix for this system of linear equations. Now notice we could start with this and go this way. So this goes back and forth. If we start here, we know the equation is, because we have a number and a number. This is on the right side. This must be an x and a y. So 3x minus 2y equals 3. Negative 2x plus 1y equals negative 2. So we can go back and forth between system of linear equations and augmented matrix. A second example. Here's a 3 by 3. Here's a system of 3 equations and 3 unknowns. Okay, we have not worked with these before, because they're very hard to solve graphically, and they're a bit of a pain to solve using substitution and using eliminations, but they're very nice to solve using matrices, which is why I'm now introducing them. Well, let's write this as an augmented matrix. I have x's, y's, and z's, so I'll just kind of put my headings up here. And I have equals the constant. Whoops, C-O-N-S-T for constant. Okay, surrounded by brackets. Okay, the equal sign I'll put in as a dashed line. Okay, my first equation has a coefficient of 3 for the x, a coefficient of negative 2 for the y. There's no z term, so that coefficient must be 0. And the constant for the first linear equation is 7. Let's look at the second equation. I have a coefficient of negative 2 for the x, positive 1 for the y, positive 4 for the z, and a constant of 2 for the second linear equation. And for the third linear equation, I have 1, 4, negative 7, 0, 1, 4, negative 7, 0. So this is the system, and this is how the system is written in an augmented matrix. 3x minus 2y plus 0 z's equals 7, etc., etc. Okay, and again, we can go back. We can look at this. We know that we have an x, y, and a z because I have 4 columns, and the last column is the constant. So I have x, y, and z. So it's a 3 by 4 matrix. All right, how do we solve these linear systems using matrices? All right, so we're going to solve a linear system using these augmented matrices. Now, there's a lot here, and if you ever take a class in linear algebra, you'll do a lot of work with matrices. Matrices can be added, subtracted, multiplied. You can do all kinds of things with matrices, and linear algebra gets really into that. What we're going to do is we're going to let our calculator do the work for us. And so to solve these using the augmented matrix, we're going to use a process called row reduction. And again, in a linear algebra course, you'll see how this actually works piece by piece. Again, we're going to let our calculator do it for us. And the goal of row reduction is to get the matrix into what is called reduced row echelon form, abbreviated RREF. If we get it into reduced row echelon form, we've solved it. And that's pretty nice. Okay, so here is our equation. Here's our system of linear equations. This is a system of 2 equations and 2 unknowns. We've solved this one several times. We've solved it by graphing. We've solved it using substitution, and we've solved it by elimination. Now we're going to solve it using augmented matrices or an augmented matrix. Okay, so we're going to now let's talk about, let's first set it up as a matrix. Okay, so I'm going to set this up as an augmented matrix. Notice it's already written, x's and y's on the left, constant on the right, x's and y's on the left, constant on the right, so that's good. So the coefficients, let me come down one more to leave some space here. So remember we have the x's, and the y's, and then we have this dotted line to help us, equals the constant. I'll just put a number symbol for the constant. So the first equation has 2 x's, 1 y, and the constant is 5. The second equation is -4 times x, so the coefficient of the x term is -4. 6 times y, and its constant is -2. So there's the augmented matrix. We're going to do what's called row reducing this. Okay, row reducing this piece and seeing what we get. Okay, so now let's get into our calculator and see how matrices are dealt with. Let me move this up. Okay, let's come into, I need to come a little bit more here. I'll come to the side, and I think I can get that in there. Okay, I'm going to come up here. You can't see that because that's, well, I think that'll work for us right about there. Okay, so you want to look, I think I have it on my screen. You want to look right here. Whoops, let me go a little bit higher. Let me start off right here. You want to look right here, and you have a blue function here called matrix. Okay, so we're going to make use of that, the menu under the matrix function. Okay, so I'm going to go to second matrix, and I can do some things with matrices. Okay, so that's one place we're going to go, is this blue function of matrix here. Okay, to design the matrix, there's a shortcut button, which is a green F3. You'll notice green F3 puts us in the matrix shortcut. How many rows do you want? How many columns do you want? And we can build the matrix from green F3. Okay, so let's take a look here. We want to do the following. We want to row reduce, or put into row reduced echelon form, this matrix. Okay, so let's first go into, whoops, let me get into here. Second quit. Whoops, second quit. Okay, let's first go into the matrix menu and go to math. And I'm going to scroll up because I need to get to RREF. Okay, row reduced echelon form, and select enter. Okay, because I want to row reduce echelon form that matrix right there. Now, second, this matrix has 2 rows and 3 columns. So I'm going to go to the green F3, and if I need to, I can select 2 rows and 3 columns. They were already selected for me. Come down to OK and click OK. And there you have it. That is the scaffold. We just need to put the numbers in. Now notice there is no dashed line here. That's to help us. But you can kind of think it's there, but that's helping us to understand it when we see it in writing. So let's put in these numbers. So 2, 1, 5 in the top row, and in the second row or the bottom row, -4, 6, -2. And then I'll close the parenthesis. So now I want to put this augmented matrix into row reduced row echelon form. Press enter. Out this comes. So what comes out? Okay, so if we go over to here, what came out is 1, 0, and I'm going to put the dashed line 2, 0, 1, 1. Okay, so there you have it. Okay, we have just row reduced this matrix to this. Okay, now, what do we have here? Okay, I want you to notice here, row reduced echelon form equals 1s on the diagonal, okay, and 0s elsewhere. Here you have it. 1s on the diagonal and 0s elsewhere. Okay, and what this tells us, remember, this is x, This is y equals number. This tells us x equals 2, 1x plus 0y equals 2 from this one. And this one tells us y is equal to 1. So our solution, using matrices, x equals 2, y equals 1, or as a point, the point 2, 1. Okay, so that's how you row reduce an augmented matrix to get the answer. All right, let's take a look at where this is really useful, which is a matrix in 3 by 3. Okay, so we've talked about that. We kind of spoke to this briefly. A linear system of 3 equations and 3 unknowns. It can be solved by graphing, but if you have 3 equations and 3 unknowns, you're talking about a 3D graph. And that's pretty hard to draw. Certainly doesn't take place on most graphing utilities. You need specialized software to graph 3 dimensions. And it's probably difficult to read. Okay? You can also solve these by substitution, but it takes a while. And you can solve these by elimination. Again, it takes a while. We haven't seen that because we're just going to focus on solving it with a matrix, because it is far easier to solve with an augmented matrix. All right, so here's our system of linear equations. In this case, you can see I have 3 equations, x, y, z. I have 3 unknowns. Okay, this is a system of 3 equations and 3 unknowns. Okay, let us do it. Let's row reduce. Let's row reduce the augmented matrix to get the solution. Okay, so we're going to, I kind of say RREF, or ROREF. RREF. We want to RREF. Okay, now we have x, y's, and z's. So x, y's, and z's. Here is our equal sign. Here's our number. And let's make sure, are we in the right? We have all x, y's, and z's on the left, constants on the right, so we're good. Let's look at the coefficients for equation number 1. 2x's, 6y's, negative 4z's. And the constant is a negative 16. Equation 2, negative 3, negative 1, and 2, and the constant is negative 2. Equation 3 has no y, so 0 in for the y, but I have 4x's and 10z's and a 13 as its constant. All right, so we want to RREF this augmented matrix, and we're going to come out with x, y, and z. And again, here's our equals. We're going to come out with this, and hopefully it's going to have 1s on the diagonal. Okay, let's take a look. So let me move my stuff out of the way here. I'm going to go up a little bit. Let's recall we first do here. Let's first go into our matrix menu. Let's go to Math, and let's select letter B, in my case, RREF. Okay, I want to RREF. In this case, now you'll notice this is 3 rows and 4 columns. So the green alpha, F3, I need 3 rows and I need 4 columns to fill in. I need a scaffold of 3 by 4. There's my matrix to complete. Let's use what we have here, right up here. Let's put it in here. So let's go with the first row as a 2, a 6, a negative 4, and a negative 16. That's row 1. Row 2, a negative 3, a negative 1, a 2, and a negative 2. And row 3, a 4, a 0, a 10, and a 13. I'll close the parenthesis, and I'll press enter. And sure enough, I got the answers. Notice I have 1s on the diagonal. I have zeros elsewhere. So this is in row reduced echelon form. And to the right side, the far right, I have my answers. 2, -3, and 1/2. Okay, so again, I'll talk here. 1s on the diagonal. So what is the solution to this? Well, the solution is x equals 2, y equals -3, z equals 1/2. As a point in three-dimensional space, these three planes, because in 3 dimensions you're graphing planes, not lines, intersect at the point 2, -3, 1/2. Okay, now if you were to go back and algebraically check, if you put 2 in for x, -3 in for y, and 1/2 in for z, it has to work for all three, and it does. I'll let you check it if you'd like to. Remember, it has to work for the solution has to be the solution for all equations in order to be a solution for the system. So there's your solution right there, 2, -3, 1/2. Very quick, far easier than trying to do substitution or elimination. Come up with an answer just like that. Okay, let's take a look at one more way you can use these augmented matrices, and we'll take a look at what happens when you have no solution or infinite solutions. Let's do some curve fitting. Example 4. Find the function y equals ax squared plus bx plus c, whose graph contains these points: 1, 2, -2, -7, 2, -3. Okay, so if we look over here, I'll make a quick sketch. Oh, that's not going to work. It's a terrible sketch. Okay, so let me see here. I'm going to just do a quick sketch of what this looks like. 1, 2, a ballpark here. 1, 2, -2, -7. I'll put it down here. -2, -7, and 2, -3, 2 about here. So we want to find an equation of a quadratic that includes all those points. Okay, we can do this using matrices. We know the point 1, 2 is on the graph, which means this point makes this equation true. So let's put 1 in for x and 2 in for y, and we're going to get a times 1 squared plus b times 1 plus c equals 2, or a plus b plus c equals 2. Okay, the point -2, -7 is on the graph, so it makes this equation true. So a times -2 squared plus b times -2 plus c equals -7, or 4a minus 2b plus c is equal to -7. We'll do the same thing with this point. If this point is on the graph of the function, it makes this equation true. So I'll put 2 in for x and -3 in for y. A times 2 squared plus b times 2 plus c equals -3, or 4a plus 2b plus c equals -3. Well, guess what? This is a linear system. 3 equations and 3 unknowns. Now we're using a, b, and c instead, but it's the exact same idea. Okay, 3 equations and 3 unknowns. We can solve this using an augmented matrix and putting it into reduced row echelon form. So let us ref And let's put this into a matrix. 1, 1, 1, 2, 1, 1, 1. There's the equal sign, 2. And we'll note this is the A, this is the B, this is the C, and this is the number. There's the equal sign. 4, negative 2, 1, negative 7. 4, negative 2, 1, negative 7. 4, 2, 1, negative 3. 4, 2, 1, negative 3. Okay, let's row reduce that to get what A, B, and C are. Okay, so I'm going to go up a little bit here, bring this in. Okay, again, I'm going to start off by going to the RF in the matrix menu under Math, RF, and I need to build the matrix. I have 3 rows and 4 columns. So alpha, F3, it's already set to 3 and 4, so I'll just press OK. Now let's enter in the first row here, which is 1, 1, 1, 2. The second row here is 4, negative 2, 1, and negative 7. The third row here is 4, 2, 1, and negative 3. Close the parenthesis, and I'll press Enter. Note the diagonal form with the ones on the diagonal, and there are my answers. So I'm gonna copy what I see here right here, so I'll put this to the side. Okay, so my reduced echelon, my row reduced echelon form is 1, 0, 0. Again, I'll put a dashed line. This is A, this is B, this is C equals number. And this is negative 2. 0, 1, 0, and this is 1. 0, 0, 1, and this is 3. So again, here is my 1s on the diagonal, 0s elsewhere. 1A is equal to negative 2, so A equals negative 2. And here, 1B is equal to 1, so B is equal to 1. And here, a C is equal to 3. So C is equal to 3. This tells me that Y equals AX squared plus BX plus C. What we're looking for is, well, A is negative 2. Whoops, AX squared. I forgot the squared here. Sorry about that. AX squared. Well, A is negative 2, so Y equals negative 2X squared. B is 1 plus 1B. I'll just write the 1, although I don't need to. Plus C is plus 3. Okay, so this is the equation. This equation should have these 3 points on the curve. Well, let's test that. Let's see if that's true. Okay, so let's go to here. Let's put that equation into the calculator. I'll move it up here so we can see it. Okay, that's a quadratic. So Y equals clear. Let's put in negative 2x squared. Here's my quadratic. Plus x. And this should be an x. Sorry about that. I have a mistake right there. That's 1x, not 1b. Plus x plus 3. Let's graph it. Well, there is the quadratic. Now, let's look at the points. Okay, so there's my quadratic. Are these 3 points on this quadratic? Well, let's go to trace. And the first one, let's put in 1. When x is 1, does 2 come out? Yep. The point 1, 2 is on the curve. Let's check the point negative 2, negative 7. Let's put in negative 2 for x and press enter. Sure enough, out came negative 7, so that's on the curve. And let's put in the point positive 2, and we should get 3 out, and it's right here using our trace. We could also, of course, go to our table and see these points as well. There's the point 1, 2 right here. Here's the point negative 2, negative 7 right here. And finally, here's the point 2, negative 3 right here. Either of those will do it for you. So you can use a matrix to also do some curve fitting. Okay, last topic. What does RF look like? Because remember, sometimes we have no solution and sometimes we have infinitely many solutions. So what does the RF look like if that's the case? Okay, now recall, no solution means that we have an inconsistent system. The lines in 2 dimensions or the planes in 3 dimensions are parallel to one another. There's no intersection going on. There's no solution. If there are infinitely many solutions, we have a consistent and dependent system, which means in 2 dimensions, the lines are identical, one on top of the other. In 3 dimensions, the planes are identical, one on top of the other. Okay, so what does that look like when we do this reduced row echelon form? Well, we're going to look at the last row to come up with how this looks. So example 5 here, let's take a look at this system of 2 equations and 2 unknowns. Okay, so again, I'm going to go to my matrix menu, go to Math, and choose RF. I'm going to go to my alpha F3 and make my matrix, which in this case is 2 by 3. So it's 2 rows by 3 columns. Now I built it, let's fill it in. 4, -6, excuse me. And 8 is equation 1. Equation 2, again right here. -2, 3, and -4. I'll close the parenthesis, and look what comes out. Okay, I have 1, -1.5. Okay, and this is 2. And I have 0, 0, 0. Okay, look at the last row. The last row says 0 equals 0. Okay, 0 equals 0. Well, we've known that. We know that's a true statement. We solved that with our, when we were doing graphing with a system of 2 equations and 2 unknowns. That's a true statement. It's always a true statement, which tells us I have, okay, an infinite number of solutions. Okay, so in this case, I have a consistent and dependent system, infinitely many solutions. These 2, in this case, they're lines because there's only an X and a Y. These are the same line from the last row. Let's look at a 3 by 3. What does it look like? What does it look like if there's no solution in a 3 by 3? Or same thing would happen. We're going to look at the last row. Okay, what does it look like if there's no solution? So I'll slide this up. Okay, I'll again go into my matrix menu, go to Math, and go up to RF, Reduced Row Echelon Form. I'll build my matrix with my green F3, and this is 3 rows, 4 columns. So I'll go to 3 rows and 4 columns, then click OK. Let's fill it in. Equation 1 is 1, 1, 1, 6. Equation 2, 2, -1, -1, 3. Equation 3 is 1, 2, 2, and 0. Close it up and press Enter. Okay, what did I get? Well, let's take a look here. I got the first row is 1, 0, 0, and I'm going to put in the dashed line, 0. The second row is 0, 1, 1, 0, and the third row is 0, 0, 0, 1. Okay, so let's take again, look at the last row. This last row says 0 equals 1. Okay, 0x plus 0y plus 0z equals 1. This is a false statement. Okay, that's never true. 0 never equals 1. So this means we have no solution to this system of 3 equations and 3 unknowns. No solution in 3 dimension tells us that these three planes that we have built are parallel to one another. There is no intersecting going on at all. So there you have it. How to use augmented matrices to solve systems of linear equations.